Hello guys, welcome back to my channel Gamma Digamma. So in this video, I said uh, let's stop with the integrals and the regular stuff for now. Let's go into differential equations. So like the title of the video already suggests, let's get started. Okay, so as I said, let's deal with a differential equation. So let me just write it down. X squared plus xy plus 4x plus 2y plus 4 times dy over dx minus y squared is equal to 0, and we have a given condition that x is always greater than 0. Okay, so how are we going to tackle this? One classic trick we can use is separate the x from the y. So if I do that, I have x squared plus 4x plus 4 times dy over dx plus xy plus 2y dy over dx, and then take the y squared on that side, giving us equal to y squared. Notice this bracket x squared plus 4x plus 4 is actually x plus 2, but the whole thing squared dy over dx, because if you expand this, you'll have x squared plus 2 times 2x, which is 4x, plus 2 squared, which is 4, which is exactly what we have on top, plus take a y common, you have x plus 2 times dy over dx being equal to y squared. So okay, now at this point what I'm going to do is I'm going to divide both sides by y squared, just for the balance, because this only has x, this has one x, one y. I'm talking about the order of terms, and here we only have like two y's if you want to talk about the degree. So when I do that, I have x plus 2 whole thing squared divided by y squared dy over dx plus y times x plus 2 over y squared dy over dx being equal to y squared over y squared is 1. So I can take this under a common square operator, plus we can cancel one y and then write this as x plus 2 divided by y dy over dx being equal to 1. Now at this point what I can do is have dy over dx common in these expressions, x plus 2 over y whole thing squared plus x plus 2 over y being equal to 1. Now I want to divide both sides by everything that is not dy over dx. Basically I want to isolate dy over dx. So I have 1 divided by x plus 2 over y whole thing squared plus x plus 2 over y. Now I would like to use a substitution that actually resembles a homogeneous type differential equation. So in homogeneous differential equations, we let v equal y over x or v equal x over y, depending on which variable we gave preference. But in this special differential equation of today, we're going to use a slightly different substitution which is actually inspired by this. So let's use v is equal to x plus 2 over y, because if I do that I have v squared plus v in the denominator. Okay, so now to substitute for dy over dx, we need to differentiate both sides with respect to x. So doing that, we have y, and the derivative of x plus 2 is 1, so ignore that, minus x plus 2 times the derivative of y is dy over dx divided by y squared. Okay, let's isolate dy over dx now. We have y squared dv over dx is equal to y minus x plus 2 dy over dx. I can actually make a substitution for y. Y from this is nothing but x plus 2 over v. So x plus 2 over v whole thing squared dv over dx is equal to x plus 2 over v minus x plus 2 dy over dx. So I can rearrange some terms. I'll have x plus 2 times dy over dx being equal to x plus 2 over v minus x plus 2 over v the whole thing squared dv over dx. So finally dy over dx, now dividing both sides by x plus 2, is 1 over v minus one of these will go, so x plus 2 over v squared dv over dx. So I want to substitute instead of dy over dx this expression over here. So now after substitution, plugging back into our original differential equation, we have 1 over v minus x plus 2 over v squared times dv over dx instead of dy over dx, and then we have 1 over v squared plus v, because of this substitution, and these two terms are the original motivation for this substitution. Okay, fair enough. Now I would like to factorize out a v. So we have 1 minus x plus 2 over v times dv over dx. Same thing I can do on this side, and I'll have v plus 1 like that. So the v's can cancel out because v cannot be 0, because v, again, by our original choice of substitution, is x plus 2 over y, and for v to be 0, x plus 2 has to be 0, which means x has to be negative 2, which is not possible because originally we defined x to be greater than 0. So this cancelling is justified, and finally we have 1 minus x plus 2 over v times dv over dx being equal to 1 over v plus 1. So if 1 minus 1 over v plus 1 is equal to x plus 2 over v dv over dx. This can be actually simplified to v over v plus 1 is equal to x plus 2 over v times dv over dx. And notice this form is variable separable. We can separate the x's and the v's. So I can take dx on that side and x plus 2 like that, being equal to v plus 1 divided by v squared dv, and integrate both sides now. Here we have to integrate with respect to x, so we have natural log of absolute value x plus 2 being actually equal to integral of 1 over v plus 1 over v squared dv. So if natural log of x plus 2 being equal to natural log of v minus 1 over v plus a constant of integration, because it's an indefinite integral here. Well, I can plug in for v x plus 2 over y minus 1 over v plus c. So natural log of x plus 2 using log properties is natural log of x plus 2 minus natural log of y minus 1 over v plus c. So these things cancel out. We basically have natural log of y plus 1 over v which I can actually express as 1 over x plus 2 over y, which is y over x plus 2 being equal to c. Fair enough. And if you want to do more justice by taking the anti-log on both sides, you can do that. So we'll have e as the base, y multiplied with e to the y over x plus 2 actually being equal to e to the c, which we can call another constant of integration d. So y is actually d times e to the negative y over x plus 2, and d, I want to remind you, is e to the c. So this is our general solution to the differential equation. And it wasn't much work actually. If you look back, the only striking and the most important part of this differential equation, solving this differential equation, was actually this substitution over here, letting v equal x plus 2 over y, and all these things just followed naturally as a consequence of that. Now, as an additional bonus to this video, I wanted to actually show you guys how the graph of the general solution looked like. So I am on Desmos calculator. You can check out these guys' website, and I have written the function down. So we can vary d, we can vary the initial condition d. So I have a range of negative 10 to 10. So let me just slide it, and you can see how the graph with the red line varies accordingly. So on this side it's almost like a part of a hyperbola, and here it's like an inverted parabola. And now I would like to impose the condition that x has to be greater than 0. Okay, imposing that, it looks like our left hand side has disappeared. So over here we just have a graph like we have for charging capacitors, or electrical components when we are trying to do electromagnetism. Basically an exponential graph, exponential build-up graph. And when d is 0, becomes like a flat line, and when d goes to negative, this actually curves like a hyperbola, and then its eccentricity varies drastically as I change d to negative. And it has asymptotes, if I'm not wrong. Horizontal asymptote here and a relatively vertical asymptote here. So that was how our general solution looks like, and we can vary d. That's how lower or higher this graph changes. So I hope you really like this video, guys. Please like, share and subscribe to my channel. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math, and peace out. Gamma Digamma signing off.